Excellent. Sam, thank you very much for the introduction. Yes, I'm going to talk today kind of wearing both hats as Chief Technology Officer at Agility Robotics, also as Professor at Oregon State in the Robotics program. I'll show you a couple things. This is Digit on the picture on the front page, the robot we are now selling at Agility Robotics. But a lot of what I'm going to talk about today is kind of the research in my laboratory at Oregon State. But kind of the difference between the two is at Agility, we are so focused on products, so focused on making something that is going to go to customers, going to be used for a job, going to be doing useful work. And of course, at the research lab, we can be looking out quite a bit further ahead and saying, this is a really interesting technical direction. We think this is the future of how things are going to work, but we don't quite understand it yet or know how it's going to work. So let's explore that. So today I'm going to talk a little bit more about the exploring that we're doing, things that I see coming down the pipeline for physical interaction, for legged locomotion, for robot control. And specifically, I'm going to talk about machine learning. Now, I'm not a machine learning expert. As Sam said, I was a mechanical engineering undergraduate, and my whole kind of skill set, my talent is in designing machines. But also understanding dynamics. And so I work with some really, really great people in terms of writing code and doing the software that controls really well. And what we're trying to do is kind of merge those things, merge our understanding of how does legged locomotion work with some of these newer tools like machine learning. But it's just one of many tools. And I don't think that you ever want to use it as a kind of a black box solve all. You just want to use it just along with all the other tools for engineering control systems. So that's what I'll talk about today. Okay. I guess I said this already, but machine learning is a great tool. It's one of many. It's not a magical box. And what I'm going to talk about for the first bit here is how legged locomotion is basically a special corner of dynamics. It's kind of a dynamical phenomenon. It's like a pendulum in the way the pendulum keeps time, or a spring mass system. Same thing. It's periodic. And I think something like that is the foundation of legged locomotion. It's not just dynamics in general, try to get robots to do arbitrary things. It's more capture this special corner of dynamics and work with it. And there's a lot you can do without machine learning. Most of legged locomotion progress to date is without machine learning. But I don't think you can do everything. I think too much of the approaches to date are model-based, and models, what do they say? All models are wrong, but some are useful. Certainly models are always simplified, and the question is how much simplified? You know, it's a reduced order model, but how simple is it? It's not capturing all the dynamics of the robot. And if you really want to get into the corners and really get into all the dynamics that a machine can achieve, I think that that's going to have to be done with strange nonlinear representations that can probably be learned with machine learning. So the question, though, really is how do you guide this learning process when we already know so much about the goal? There's a lot of science we know about legged locomotion. So how do we then incorporate that and steer our learning process given what we know? Okay. So to start with, here's the hypothesis, right? Legged locomotion is a dynamical phenomenon. It is in many ways analogous to a clock. And I would call that, what I mean is it's dynamics that exist. These are just physics that exist combined with engineering. Now, early on, Galileo just made the observation, hey, if I swing a weight from a string, it's isochronic. It keeps time no matter what the amplitude is. The frequency stays the same. And that's a really interesting observation just of physics. But it was not until, I don't know, 100 years later that Huygens actually did the math and say, actually, you need a cycloid shape in order for it to be actually isochronic. You know, here's the actual solution. Here's the absolute, correct, perfect solution. And I think where we are today is more in the Galileo side, where we've kind of made some observations that, this spring mass behavior really gives us some stability. And here's a simple model. This is very much a reduced order model. But it describes some really interesting things that we observe in all animal locomotion. It's very, very self-stable. It's very robust. There's a lot about this that is really interesting that we think is kind of this is a special corner of dynamics. This is sort of like a discovery. But again, I think this is kind of the Galileo version of the pendulum, where maybe this is capturing 80% or 75% correctly what's really going on. And we have yet to understand really what is the full perfect picture of this dynamical phenomenon, or how to utilize it. That's okay, still useful. And then I talked about engineering to capture the dynamics. If you think about a clock, it's not just a pendulum. You know, you have to add energy to it. You have to count up the number of swings. You have to create a readable interface. You have to figure out how to insulate your pendulum from all the friction and all of the interference and all of the dynamics of your gears and things like that, or the weight or the temperature effects, air pressure, all the other things in a clock. So hundreds of years of engineering went into making clocks decent timekeepers, with the pendulum anyway. And you know, eventually, of course, they went to quartz crystals, which are oscillators in electronics and so on. But let's ignore all that for now and just talk about the special corner of dynamics that is a pendulum, and how the analogy between that and legged locomotion. By the way, I welcome anybody to speak up and ask me a question. All right, I think I've left plenty of time in this presentation for questions, so just let me know.
Yeah, I apologize. I forgot to mention those logistics. And I'm monitoring, you know, the participant window in the chat. So if folks have questions, they can type them in there or raise their hand or things like that.
Great. Okay, so legged locomotion is a dynamical phenomenon, something like a clock, but there's a ton of engineering you need to do. And here's some of the engineering to capture the dynamics for legged locomotion. Now, early on, what we did is we said, okay, I think we understand that this spring mass model is at least close, right? It's something, it's not just a descriptive pattern. It is very close to what the actual physics are that give us stable behaviors and robust behaviors and efficient behaviors on animals, and then, you know, should be able to do on machines. So we designed Atreus, which is an acronym for assume the robot is a sphere. The whole idea is to build a robot, build a machine that is as close as possible to this simple math model. And early experiments here, you can see the force and the ground reaction force when we pick up the robot and throw it in the air. The motors are turned off, it's just going to bounce a few times, and we're getting pretty close to the ideal spring mass model. The green dashed line is the simulation, the orange line is what the robot actually did when it landed on the ground. So we built something really close to a spring mass model, okay? Then we built it into the full bipedal robot, and we were able to get Atreus to do continuous transitions through the speeds between walking and running, which reproduced exactly what we saw in simulation. Very early on in the program, we were able to walk and run over all kinds of terrain, unexpected step ups and steps down that were significant fraction of the leg length. It didn't matter what surface we were running on, so grass or pavement or soft foam. It was self-stable. It just shrugged off all of those sorts of things as a dynamic behavior. And so this was a really important demonstration of the idea that we are in a special corner of dynamics. It's only dynamics that is causing this robustness. There's no planning, there's no perception, there's no decision making. It's just a spring mass system with very simple controllers on where it's going to place the feet in order to stay balanced. And then there were a bunch of other things that were pretty important about what happens at impact and what is your behavior going to be through that impact. And that's why there's giant physical springs on Atreus. Although, you know, you could do it through actuators if your actuators are good enough. But you still want your behavior to be a certain thing. You still want your the dynamics that you engineer, however you engineer some behavior through your actuation and your passive dynamics to be something when it's going to encounter or impact the ground. It's a holistic design. And so you can see here the ground reaction forces of Atreus running over the force plate, and compared to my graduate student at the time, Christian Hubicki, who's now a professor, running across the force plate, you don't see a huge difference. At least the high level structure of what you want to see is there. So that's good evidence that this is on the right track. Okay, so that was a good science demonstrator, Atreus was. We then started going towards robots that are a little bit more useful with the Cassie robot, which we sold to some of the top universities through Agility Robotics. And now with Digit, still capturing the same physics that we understood from Atreus, but adding quite a lot of perception arms so you can balance when you're walking and other things. Kept with the same physics, but lets you do a lot more with it, like you'd want from a real robot. So I talked just a little bit about the actuators, and I think this is an important point. Actuators have dynamics. They are a physical thing, and they are definitely not what you want them to be. So a lot of the machine learning demonstrations and simulation or control demonstrations for legged locomotion have been with simulated robots where you can apply the torque that you want at every joint. And that will never happen on an actual real robot. In addition, the actuators, especially the ones we use, the electric actuators, have a lot of what we call reflected inertia. And so that just means there's a huge, when you instantaneously change the speed of the output by a small amount, the motor itself, the rotor, has to change its speed by a very large amount because there's a gear ratio on it. And that reflected inertia of the rotor spinning up that you feel through the output can be very, very large. It can be on the same scale as like the mass of the entire robot. So when you take a robot that maybe has a 100-to-1 gear ratio, like a harmonic drive at the knee, and you were to lift it up and drop it on the ground, you're basically causing an inelastic collision between the reflected inertia of your motor and the mass of the robot. And it doesn't matter what software you write. It's going to be that way because it is physics and it just exists in the hardware. So really what you've got to do is deal with that. You can add compliance, you can add dissipation, you can add passive dynamics. Those things can help or harm. But if you can eliminate as much of the actuator dynamics as possible, that always helps. So when you see like the Boston Dynamics Atlas doing backflips, that's just fantastic. And they've achieved that by making extremely transparent actuators. They're hydraulic actuators with a very high rate feedback, allows them to do the dynamics they want in software. There are a lot of drawbacks to that, like energy use, but they do get the performance out of it. Our approach has been focused on electric because of the efficiency, because of the cost effectiveness of it. And I think that at least understanding the passive dynamics or understanding the actuator dynamics and then integrating passive dynamics to help get the behavior that you want is very, very feasible to do everything we would want to do with these robots. I guess another thing to mention is muscles have actuator dynamics. And I think it's becoming more and more clear that the dynamic behavior of muscle is not necessarily optimal for the behaviors that we want. They may just be limitations of the biomechanical process that allows muscles to do work on the world. Certainly, there are a lot of adaptations in animals with structures like tendons and the way the muscles are configured and shaped on joints that clearly alter and vary the dynamics of the muscle. So it is absolutely, in an animal, it is absolutely not all software. It is not something where you're sending muscle commands to have your arms and legs do what they want. There's an immense amount of passive dynamics designed and built into all animals in order to create appropriate dynamic behaviors. Okay, so a little bit more about this, designing around the actuators. Transparency is key. And transparency, I would define as in software, you command a torque, and in hardware, you get exactly that torque. And that's at all frequencies, that's at all amplitudes. So if you command 500 newtons, you get 500 newtons. If you command 500 newtons at, oscillate between positive 500 and negative 500 newtons at, 5,000 hertz, you get it. And obviously that's not possible because of the inertia associated with motors and electrical dynamics and everything else. So if you can reduce your reflected inertia, make your motor rotor lighter, make your gear ratio smaller, find a way to get enough torque out of something, without having a big gear ratio, eliminate friction, have a completely transparent, efficient transmission. Things like cable drives. We got something like 93, 94% efficiency in the cable drive on some of these early robots. That's great. There's other drawbacks to a cable drive, but a harmonic drive, they're 75%-ish, something like that for friction. And that can be really limiting if you're trying to apply forces to the world because you don't know what force you're applying. I'm getting a question from someone, what would I like to see from the future of electric actuators? The best way, so Ghost Minitar is a great example of a direct drive robot. And at a very small scale, you can do that. You can have relatively very low inertia and relatively enough torque to do what you want to do and get that robot to leap and jump and do all kinds of things. As you scale up, especially to something the size of Cassie or Digit, you know, the torque from your motor goes up by the square of the surface area that you're getting on your magnets, but the mass of your robot goes up by the cube because it's volume. And so the larger machines, you just can't, you have to put a gear ratio in there. And that gear ratio gives you inertia, it gives you friction, it gives you a lot of other limitations. And that's why we add the big physical springs on Atreus. That's why we have springs on Cassie and Digit. We also are handling, you know, the foot contact. How do you interact with the ground when you make contact? So a lot of engineering that goes into what is impeding our transparency. And so in my opinion, the best solution is to have transmissions that are very, very efficient. So very, very low friction, meaning that you can command the torques that you want and you're going to get them. And then ways around the inertia problem, ways to handle the impact with the ground that mitigate the inertia. I don't know, it's just my current guess right now. Let's see, what else can I say on this slide? I'll say that early on, it was an interesting observation that if you have some sort of clock cycle, say your controller is only operating at 30 hertz, and you know, obviously control systems can run at 24 kilohertz, at 2 kilohertz easily, but you can't really perceive your environment. Sensors are always noisy, late, and wrong. And so it's very, very hard to plan exactly what you're going to do through some sort of impact or contact with the ground. But if you do things like have a clock-based feed-forward cycle based on kind of what you expect to happen, and have that clock-based feed-forward plan in series with a big compliance, you know, we found that's very self-stabilizing. In other words, if you hit a little bit early, or you hit a little bit late, or you hit ground that is too hard or too soft, the immediate reaction just from the dynamics of that clock in series with the spring is stabilizing. It is going in the right direction to cause your ground reaction forces and your center of mass motion to go in the right direction. Then you can react fairly slowly, but creating that stability as an inherent part of your system is what's important here. And boy, there's a lot to solve there, a lot of science still understood. Okay, so I talked about the dynamical phenomena of legged locomotion. Maybe another way to think about it is it's some sort of periodic attractor. And when I talk about a planar pendulum or a spring mass system, of course, that's a 1 degree of freedom system. There's really not a lot you can do to influence that system. It's just 1 degree of freedom. It is stable. It keeps time. But I think legged locomotion is many more. Maybe it's 7 degrees of freedom. I don't know, as a periodic attractor. And there's a couple of degrees of freedom in that periodic attractor. So instead of just a back and forth of a pendulum, maybe it's more like if a spherical pendulum had some stability region for it, but it's a 5 or 6 degree of freedom or more. And now you want to kind of choose what's the action space. What are the inputs to this system that allow you to land on stable cycles that you would want in different directions? And one of them for sure is transitioning between the gates. And maybe that's how much energy you add, or maybe it's how you change your clock cycle in order to scale between them. But whatever gate you land on is still a stable, self-stable periodic attractor. Just you've got this degree of freedom. Now, another one might be like stride frequency and stride length. You know, I don't know the answer really. But I picked up this cool picture from Wikipedia of what an attractor looks like. That's obviously more than 1 degree of freedom. And we are kind of coming up with, I would say, incomplete and not quite correct heuristics that get us pretty close and are able to start really exploring some of these behaviors. Someday we're going to have the complete picture of what this looks like. So just to start with, I want to point out Cassie, Atreus, all of our robots can certainly walk without learning. We have a clock cycle in them that is kind of like our feed forward behavior. We have a plan In other words, we know that we want to go right foot, left foot. We, in this case, have no information about the world, but we can have information about the world, and that's what the planning does. We have a reduced order model inside that allows us to make choices about, say, where to place the feet in order to stay balanced, and an optimization tool so that you can basically map this very complex robot with lots of joints and more joints and more behaviors possible than the reduced order model will enable, but optimize for your priorities so that you actually get close to what your reduced order model is saying. And so here's Cassie just walking over some unexpected terrain and handling it pretty well because of the transparency in the actuators. So you'll see that the robot maybe steps up a little bit, but at first when it steps on these, the leg kind of squats a little bit. The leg just kind of takes that obstacle. Think of it as force control. If you're applying a certain amount of force on the ground, then the deflection of the leg doesn't matter. And that's kind of what's going on right here. We have a priority for how much force we're going to apply, and also a small priority for position, because say you know exactly what force you want to apply, but you've got a tiny error in the force you're applying, the robot is either going to sink to the ground or accelerate up continuously. So you do want to have some priority as well on the force that you're, or the position that you're where you are. And that's what I mean by optimization tools. We've got several different goals. It's balancing between those goals, kind of trying to optimize for things.
Hey, Jonathan.
Yeah.
Can I ask a quick question?
Please.
With respect to your point about Legged Locomotion being a dynamical phenomenon, can you comment on the sort of anxious pace that Cassie does even while stationary? So what? Yeah.
So Cassie can certainly stand, but our controller has a clock as part of its foundation. And so really it's walking at zero velocity when it's stationary, because we turn on the walking gait and the walking behavior. And then we can just change its velocity. It changes its foot placement in order to go forward or backward at different speeds. That's all it is. I don't think that's necessary. It's just that's what our controller is doing right now.
No, that makes sense, because you're just getting ready to steer it. You're getting ready to drive it, right? So.
Yeah, and so this is very manual, right? So the operator is saying on his controller, okay, turn on walking gait behavior, okay, change speed forward, backward, etc. There's not a lot deeper than that that's going on here.
Cool.
But what I would like to be doing is, going towards this kind of periodic attractor, which probably has a zero energy point too, that's also stable, which is standing, which probably looks a lot like zero moment point control. It's just using ankle torques in order to stand in one place. But that, I think, is on a continuum along with the walking, running, hopping, skipping, jumping, and all the other things. I just don't think we've figured out how to implement that well on hardware.
Got it. And then there's a question in the chat following mine about slippery surfaces. How does it behave on oiled floors?
Same way as a person, just falls right over. So we do have kind of an estimate of the friction cone, and that informs things like one of the early lessons we learned is you don't use a toe switch. You don't know when it's on the ground. You have some stochastic estimate of when your foot's on the ground or not. If your foot is in the air, you want to be placing it in a particular position so that when you do land, your foot's in the right place. But then when you're on the ground, when can you start applying forces in the XY, in the fore aft? When can you rely on the fact that your foot's on the ground and you can apply lateral forces? It's really only when your vertical force starts to increase, and we have some estimate of the friction cone. And so there's a big gray area, the first and last 10% of stance phase. You don't really know, and your controller doesn't really know or rely on whether you're on the ground or in the air. And so there's kind of a point where the swing phase and the stance phase are kind of separate controllers, but kind of tangent to one another. So they're both kind of trying to do the same thing for that 10% overlap at the beginning and the end of stance. And the behavior changes a fair bit if you modify your estimate of the friction cone. So that's, again, something that kind of fits into one of the optimizations is, estimate of what you think your friction cone is. So if we wanted to walk on ice and we were able to perceive that it was ice, that's what we would do. We would modify the friction cone. The robot would likely take much shorter steps because it knew it would not be able to take a big step and rely on that friction existing. All right, so I also just want to show a couple of brief, these are the only two videos I'll show of Digit walking around outside. It's the same configuration of legs as Cassie because physics is still true. The reasons we designed the legs the way that we did are still the case, although there are a lot of differences internal between the Cassie and the Digit legs. And so building on the locomotion, which we really have not been paying a lot of focused attention to because we've been really working on incorporating, using the arms to swing, using the arms to manipulate the world and balance the robot with the different masses of things that you're picking up, catching the robot when it falls, reorienting to get back up, starting to add in perception. The robot here is using those QR codes to identify where the table and the box and everything is in the room, using the LiDAR to avoid obstacles. So starting to build a much bigger stack on the foundation of the basic locomotion that we've got. There's so much room for improvement in absolutely everything that the machine does. We really have to pick and choose what it is that we're going to be doing. So the thing that's nice about learning, as I mentioned earlier, is it gets into the corners, I would call it. And what I mean by that is that when we're controlling Digit, when we're controlling Cassie, we're relying on some reduced order models, and that constrains our behavior. There's a real constraint. But if in this video I'll show, we started with an initial trajectory seed, and this trajectory came out of Cassie's traditional controller that we'd already created. And we tried it on the robot for the very first time, and it worked. We were able to do the simulation to the real transfer. I think a lot of that has to do with the correlation between the robot's behavior and the simulation's behavior. It also has to do with the self-stability of kind of the behavior we're trying to create. The robot is roughly a spring mass system. So inherently, it does have a lot of those stabilities that we talked about that I talked about early on in this discussion. But we're not really explicitly utilizing them. We're kind of accidentally utilizing them in this. And it is a pretty brittle solution. This running gait, I love it. I think it looks very biological. I really like it, but it does fall reasonably easily. It's very sensitive to the friction cone on the feet right there. So this behavior worked on the treadmill, but when we did it on the road, even the crown of the road, it was falling sideways. It would twist its feet when the feet would just slip and twist on the ground when we were on pavement, and this would fall over. So this particular initial idea kind of was pretty brittle, but what a dynamic behavior that we couldn't achieve without learning. So I'm actually taking longer than I thought to talk. I'm going to have to move along a little bit here, but the question is that how do we guide the learning process when we already know so much about what we're trying to achieve? And there's a couple of ideas we have in that lab, starting with learn a gait library, and then use this reduced order model both for training to give you all of the different range of different gaits and also for control. It's a way to have that input. What's the action space? We can actually use our reduced order model to go through the range of different, trot. Well, I guess with a biped, it's just walk, run, skip, jump. But working towards having real-time model predictive control using that reduced order model. Now, the next idea is let's learn in task space, since that's the common language. What should the feet be doing? What should the center of mass be doing? We already know a lot about the robot, and we already know a lot about how to coordinate the joints. So why would we relearn how to do all of that and put the burden of the inverse dynamics and inverse kinematics on the learning system? We can just put that in there and learn in task space. And the next idea is, okay, forget reference trajectories, forget even models. Let's see if we can describe everything we know about legged locomotion through the cost function. That gets some interesting results if you're very careful about it. But then kind of back to a little bit of a middle ground, that clock seems to be really important for periodic behaviors. Can we give it a really simple trajectory, which just a clock signal basically, but describe legged locomotion by the cost function, and where do we get with that? So this is the first learned policy on Cassie in collaboration of Michael Van de Pan and the University of British Columbia. And kind of like the running behavior I just showed, it's bootstrapping from a single expert reference trajectory. It's just giving it position trajectories, which in my opinion is a very, very incomplete description or even hint of what's important. Because certainly if you hit the ground a little high or a little low, or you have a slightly different environment that you're encountering, you don't want to be running that original trajectory at all. That would be a bad choice. So it's bad information to bootstrap from. Nonetheless, we were able to get some pretty good results, but only for this kind of single behavior we were creating. And it did give us some interesting stability and robustness. I don't know why, but it did. So the next idea I mentioned, right? Let's use a reduced order model. Let's create a whole library of hundreds of different gaits that come from or inspired by different gaits from the reduced order model. And here we're giving it a lot more information than just trajectory. We're giving it the pose, yes, but we're also giving it the velocities. So we have an idea then of the forces that are being applied, because that model has those physical springs built in. And then we are, in this case, just commanding the set points to the individual joints. The individual joints have their own PD controls that is known by the control system. And so this is sort of like a really fancy clock in series with some compliant behavior. The proportional gains in the controllers and the physical springs on the robot are a compliant behavior that are very approximately something like the spring mass behavior. And this worked. This worked pretty well. In this video, we just show the clear correlation between what the reduced order model is showing, what the simulation did, and then what we were able to do on the hardware. So this continues to be work in progress. It's aiming for IEEE right now. Now, the next step with this is, instead of having a gait library, do something that's a reactive planner, something that has some perception of the world, chooses what it's going to do at the reduced order model level, and then has the motion command. I don't know if I would even call it a motion command. It's more like what is the state of the reduced order model? What forces, what is the set of dynamics that you're trying to create? You know, what, if the foot is about to impact the ground, where should it be? Approximately what force do we want to be applying at the given point in time? And if the ground, you know, impacts the foot at some point, how do we want that foot to react? What kind of impedance would we want it to have at that point in time? So that's a lot more information than just a position trajectory, because we are creating a dynamical behavior here. Okay, so then the next idea I mentioned, why would we learn all the joint coordinations independently if we actually kind of have a lot of information there? And sure enough, when we learn in task space, using these reduced order model kind of thing, it does learn a whole lot faster. It doesn't have as much to learn. And it is successful in doing some nice walking gaits. You know, this kind of looks a lot like that spring mass behavior, but it learned it pretty quickly. So I think there's a lot of promise here too. I don't know that we, you know, the inverse dynamics, the inverse kinematics that we calculate for the robot are certainly not perfect, because there's a lot of unmodeled dynamics going on in the hardware. But this is showing that we're able to sort of split things out in terms of how we tackle a particular problem. This is just a small part of the overall control system. And when we're learning in task space, we're speaking a common language that works with any sort of model-based planners or controllers. It also can speak with a separately learned policy, which would do all the inverse kinematics, for example. And so we're kind of choosing to have a control hierarchy that differentiates things out so that the learning problems are much, much smaller and can find much, much more precise or accurate representations in their very small domain space, instead of trying to approximate some very, very big set of dynamics. So I think that's the power here, is just splitting it out into a series of much smaller and more feasible problems. Now, rather than maybe a trajectory or reduced order model providing dynamics guidance, the question is, can we just describe that behavior we want with really good cost functions? In our lab, we've done spent a lot of time kind of writing down from first principles, what is legged locomotion? And it's tempting to say, oh, the spring mass behavior captures it, but it doesn't. It's just that happens to be a model that gets close to what it is. But what is factually true about it? There's a lot that we can say about it. 1 foot on the ground at a time, or what's the smooth force trajectory that you would want to see, and we write a lot of that down and then try to put that into the cost functions. So it's really challenging, by the way, to start with physics-based stuff, what we think about our how legged locomotion works, and translate that into cost functions that are in the language of machine learning. But we made some progress. We got somewhere with this. And here is a non-reference-based reward, no trajectory, no prior behavior that we gave it, just describing it in terms of the cost functions. And we got the highest speed we've been able to show yet. This is actually faster than the running gait that I showed at the beginning. I like the running gait, but this is faster, so not too shabby. All right, so the next idea. All right, we are describing all of our behavior through cost functions, but kind of pick a middle ground here. Let's give it a little bit of a hint, a little bit of information. We don't actually know what an optimal trajectory should be. Maybe the reduced order model is kind of too constraining, or I don't know, we could do it in a much more computationally simple way. And so that's what this effort is. It's choosing a set of clock inputs that are very easy to modify, that are very convenient for the learning policy to utilize, and much, much more computationally effective than using a reduced order model. And we were able to get some really surprisingly good behaviors out of this, just choosing the duty factor of which foot is on the ground and when. And here's some transitions between gaits. By the way, we haven't shown any of these videos. This is the first time I'm showing these videos publicly. Some of these results are just from the last couple of weeks. But here's Cassie hopping, and it'll do a transition from hopping to walking gait, and then do a little bit of galloping, and then back to a stand behavior. All of these were learned in simulation and then tried on the robot. There's no online learning with the robot. All the learning is done offline. And that's what it looks like standing, right? We're still working on having that clock come down to 0 amplitude so they can stand in place. And this one is pretty cool. There's no good reason to skip, but we can. Change our clock cycle a little bit and make the robot look very happy. It's a nice sunny day outside. Off we go. We need to get a red hood for the robot in a basket. Oh, okay. I didn't cut out the fall. So when we're doing the clock cycles, we can do a couple of different options. Here's a transition for the 2 beats. So really we can only do walking or hopping when we have just the 2 beats for the gait transitions. But we can do the transitions between them pretty smoothly. And then if we increase the number of beats to a kind of a 4-beat transition, we can include a couple of other gaits like the skipping behavior and a gallop behavior, and transition between all of those. So this, by the way, is not task space control. This controller is learning all of the coordination between the joints. It takes quite a long time to train in order to do that. I'm sure we can do better if we split things up a bit, but getting some decent results this way too.
I was curious about this before, actually. Do you have like a 1-sentence, what is the class of algorithms you're using to do the training?
It's a good question. The focus of this research is not on that. We're using old, classic, decade-old kinds of algorithms. There's not a lot of innovation on exactly what algorithms we're using for machine learning. The innovation is entirely how do we structure the problem and how do we engineer it. I think this one was with recurring neural networks for some of these behaviors and for the skipping behavior. But there's also just feed-forward networks that have no internal memory whatsoever. It seems like we're able to be successful with using a number of different approaches, and maybe that's less critical than setting up the structure of the problem. So I'm getting close to kind of wrapping up here. I want to point out there's an awful lot of testing, an awful lot of falls, and man, a lot of these have nothing to do with the learning policy. A lot of these have to do with the state estimator was having problems, or a part broke, or in this case, whoever was controlling the speed on the treadmill wasn't on top of things. There's a mechanical failure. I love that one because it accelerated. It's basically getting a big shove if the treadmill stops, and it didn't fall. It kept running forward. One of the problems we were having this day filming was actually data logging. Every now and then, it would just pause the control outputs and the torque commands for a quarter of a second while it was trying to save a bunch of logging data. And so that caused a bunch of these falls. You could see that leg just pause in the air. So having some hardware that's reasonably tough, that's pretty important. Having the support at Agility Robotics that's able to fix things, that's been useful. There, that leg just paused and just didn't come down. You know, the controller was telling it to, but the log files were being written. All right, so I'll finish there. Thanks for listening. I'm excited to answer some questions now.
Okay, that's fantastic. Thank you so much, Jonathan. That was a spectacular, gallery and constellation of ideas, and just awesome results. There was, I want to go to what I think will be probably a quick question, and also just give you the opportunity to do a plug. There was a question kind of halfway through, when can I buy one of these? So like more generally, like what is available from Agility? What do you want to say about that to the people?
Sure. So we sold CASI robots to some of the top universities in the world, and we are done selling CASI robots now. We've sold about 11 of those. So when we started the company, we were about 3 people is when we sold our first CASI robot, and built the company on a kind of customer-centric building products and supporting them, making sure our culture was behind that. And now we're selling these digit robots, which frankly are a lot more capable than CASI. They have the arms and the upper torso and the sensors and everything, and we're selling them for the same price that we sold the CASI robots. We're selling these at $250,000 a piece, and you can buy them now. We are selling to the academic market. Really, our focus is working with corporate customers. We're aiming for the logistics market. We have these robots carrying packages around, and there's a ton of backroom kind of work for carrying packages forward to the customer counter, doing package sorting, stacking totes, a lot of the kind of classic 3Ds of robotics, dull, dirty, dangerous kind of work that still exists in a human environment. They haven't put in purpose-built, customized automation for it yet. And so Digit is kind of perfect for sifting into a lot of those kinds of very robotic jobs that haven't yet been automated.
Awesome. Cool. So maybe, perhaps not. I don't know. I don't personally know the person that asked the question. Maybe out of reach for the private consumer at the moment, but
yeah.
but the research or industrial customer is definitely there. That's awesome. And then there was an earlier question that I elected to kind of defer that Joey wrote out, and Joey can feel free to chime in. But let me see if I can. Let me see how well I can capture the question. So. I think if I understand the question, I think it's more directed at how does the class of behaviors you want a robot to perform, what does that tell you about the design of the robot?
Oh, that's a great question. We've been studying legged locomotion for decades and building on a whole community's worth of research in biomechanics and in robots. And I think a point I want to be clear about is I feel that we are discovering this dynamical phenomenon. And that's different from saying, I'm going to design this cool widget. Legged locomotion is not just what your imagination says it is. It is a special corner of dynamics that you need to be able to utilize. So knowing what we know is an input into the mechanical design, into the actuator design, into the controller design, into everything about the machine. And we have, of course, we have used machine learning in any sort of the mechanical design. I imagine someday that could be a part of it. How can we optimize something about the spring function in the end effector of the leg that's going to optimize for some behavior? We're going to see what the dynamics are that we want, which dynamics ought to be on the side of the hardware and which dynamics ought to be on the side of the software. To date, though, it's like we know we need compliance in certain directions. We know we need transparency in our actuators. One of the reasons the leg on Cassie and Digit is configured the way it is antagonistic work. It's how much negative work does a motor do? And that's configuration dependent and task dependent. So Atreus, as an example, has to have the motors apply equal and opposite torque to extend the leg. But to swing the leg forward, both motors are applying the same torque at the same velocity. So what happens then is you've got opposite torques, but velocity is in the same direction. One motor is doing all negative work and one motor is doing all positive work. And so there's just this work loop where one motor is acting like a brake all of the time through all of the behaviors. And the other motor has to do all of the work on the world, plus all of the work to overcome the braking of the negative work motor. And that's just a configuration choice. So the Cassie leg and the Digit leg avoids that negative work loop for the task of walking and running behaviors. So
walking and running forward
or backward.
Okay.
It's just that we split up so that applying torques is one motor and applying velocities is another motor to oversimplify things a little bit, so that you don't have them doing work against one another all the time. So there's just a lot about that kind of thing where you know your behavior, you know your task, and you know the dynamics you're trying to engineer. And then it's a fairly complex engineered system top to bottom, but we have a whole bunch of guidance there. Does that answer the question?
If I can just ask like one small refinement. So I'm wondering, like, suppose you talked a lot about maybe discovering these periodic attractors or like these dynamical descriptions of behavior. So like, suppose that like you discover a new one, or like that there are many more important degrees of freedom. So is that information more important to informing the design of the robot or the design of the control? Like, how do you distinguish between those two things?
Well, so you're trying to design a set of dynamics, and think of it like a control hierarchy in some sense. Like when you're riding a bicycle, the bicycle has its own dynamics. And if you take a bicycle and you just roll it in a parking lot, and somebody, Andy Arena and Steve Collins did this experiment. Someone runs up and gives the bicycle a shove sideways. It tips over, the steering wheel tips in that direction, and then the contact patch of the wheels moves underneath the center of mass of the bicycle, and it self-stabilizes. So if it's rolling forwards, you give it a sideways shove, it self-stabilizes. And you are relying on that self-stability of the bicycle in order to ride it. Now, you can make an unrideable bicycle by changing the pitch of the steering column. And then you can either balance on it or steer, but you can't do both. I think there's some analogies in aircraft. Some aircraft with a big dihedral wing gives you a lot of stability. In that case, it's a trade-off though, because fighter jets and things that need a lot of agility have the inverted wings, so they're really unstable, and they always have to stay. You have to really be on top of it in the controls in order to stay stable. So I don't really know how to answer your question. It is a big, complicated engineering problem, and it's an engineering choice to decide what is the set of dynamics that your hardware has that you then are constrained to. Now you must work with the dynamics of your hardware, and then your control input is able to work with that. So I kind of imagine it like if you're thinking of the 5 or 6 layers of a control hierarchy, which are all divided by control rate, but also information content. at some level, you have a dynamical system that really captures something like the spring mass system, but in 3D, but also handling contacts and impacts, and also including your actuator dynamics and so on. You've created a set of dynamics. You've got a whole range of behaviors that you can now, maybe 5 different degrees of freedom as an action space for inputs into this to have your attractor land in different cycles or different behaviors. And I think there's going to be a lot of choices about how you design your hardware so that your behavior is above or below, that line. I don't know, not a very satisfying answer because I don't know the answer. And I think there's still a lot to discover.
Thank you very much.
Mm-hmm.
Cool. We may have time for just one more question because I know Jonathan has a meeting at 11:30, and I saw Kat Steele's hand up, so I'd like to give her an opportunity.
Do Megan's question first. It follows on nicely. Megan asked in the chat, could the robot adapt to altered dynamics? For example, if it sprained its ankle?
I mean, if you're aware of it, a robot typically isn't. So when the ankle loses its actuator direction, it stumbles in a weird way. It treats it like a disturbance every single time. It never plans for it. Now, I will say that with Digit, we're a lot more able to identify failures in encoders and sensors or actuators and things like that. And then, yes, the optimizer very quickly adapts to it. So, for example, if you're walking along and the arms are swinging because one foot is on the ground applying force to the ground, the other leg needs to swing forward to its next position, that's applying torques to your body. What are the best inputs in order to temporarily mitigate those? It's swinging the arms, that inertia. And if you are carrying a box and the robot knows the mass, it works right into the optimization to swing that box an appropriate amount. Or if you actually remove one of the arms, the optimizer very quickly is able to just compensate for that. The other arm swings a lot more aggressively and more across the chest a little bit. So in some ways, yeah, it definitely does adapt to altered dynamics as long as it's aware of what they are. Something like removing an arm, it knows what the arm's dynamics are and it's able to adapt.
Very cool. And that's why I love some of your failure videos. It looks like there's enough time, so I'll ask my question then too, which is also related to the legs and the feet. So can you talk a little bit more about the design choices around the feet? You mentioned a little bit how, especially Cassie, they're so small and rigid. It looks like Digit is a little bit bigger, but I'd love to hear more about that process.
Good question. So early on, we built a spring mass robot, Atreus, and it had no feet whatsoever. It had a rubber nub on the end of each foot because you don't need feet in order to walk or run. It's just not necessary. But one of the biggest failures is the robot rotating sideways, and then its velocity and its orientation are no longer aligned. And so it got up to speed running forward, but now that velocity is pointing sideways relative to the robot, and it's trying to sidestep frantically to keep up with that speed that it had, and it falls right over. So we had to add little kind of passive feet with a little bit of foam just to try and keep the feet roughly flat when it was in the air, so that when it placed the foot on the ground, the foot would just slap down on the ground, but prevent the robot from torquing too much, and just to provide a little bit of yaw control. Now with Cassie, and that's one reason Atreus could never stand, is because it had no ankles. Now Cassie has ankles, but only in the fore-aft direction, so it's like walking on ice skates, perhaps, where you can stand if you've got both feet down, but of course, if you only have one foot down, you're falling to the right or left at all times. So one of the drawbacks to that actually was, I might even have that video here. Oh, I don't, unfortunately. We were doing the testing with the early version of Digit going up and down stairs. And because you have no way of controlling the center of pressure under the foot, even a little bit during stance, you are always falling, and you're going to need to get your next foot down pretty quickly. And the longer you take to get your foot down, the farther away you're going to have to put it in order to make a correction. So going up and down stairs, you have to go fast. You can't go up and down stairs slowly because you have to place your foot really quickly. So adding the second degree of freedom in the ankle is a kind of a pragmatic choice where we're kind of wrapping in some of the traditional humanoid zero moment control kinds of ideas here, so that throughout all of stance, you can apply some torque and just correct some of the small errors of where you placed your foot placement. It's another control input that allows you to go slower up or down stairs. However, now the lower feet are getting pretty heavy. And you know, it starts to get pretty clumpy, and we start to have to think about how are we going to deal with that inertia on that contact point. And so some of our research has been understanding that and figuring out how to handle that impact with the ground while still enabling the mass of that, inertia that we're adding to the end effector. Certainly human legs have a lot of mass compared to something like an ostrich, but our feet are pretty different from an ostrich as well. Also, ostriches can run 30+ miles an hour, can do a marathon in, you know, some ridiculously short amount of time. I want to say 40 minutes. I can't remember the exact number, but they're much better for long distance running over terrain than we are. Anyway, that's a bit of a story about the feet and the evolution of our feet, and they're going to keep evolving because there's a lot of interesting dynamics that happen in the feet during contact with the ground and for adding energy into a gait or behavior, and it really influences what we may want to do with leg configurations in the future.
I just like to try to ignore them myself, but even
yeah, me too. That's why we started with the ignoring feet. That's what we've been doing for the past 10 years.
Yeah, great. Thanks so much, John.
Mm-hmm.
Okay, fantastic. I want to be respectful of our speakers' time and schedule. But again, Jonathan, thank you so much for sharing this super interesting work with us. It was a real pleasure.
You're welcome, and thanks everybody for the great questions.
Awesome.
Right,
bye, everyone.
Talk to you later.